Hello and welcome to this lecture in the course of Secure Systems Engineering. In today's lecture, we will look at exploits that target the heap. So as we know, heap is essentially a pool of memory present in the processor's address space where dynamically allocated memory resides. So every time, for example, that we use a malloc in a C program, a chunk of memory gets allocated in the heap. And when we free that memory, then the chunk of memory gets freed. So in today's lecture, we will actually be looking at how this dynamically allocated memory, or in other words, how malloc handles or manages the memory that is present in the heap. So let's just look at this motivating example. So we have a small C program over here, and what we have here is an invocation to malloc which requests 256 bytes. So when this malloc gets invoked, as we know, in the process address space, a chunk of memory of the size which is approximately 256 bytes would get allocated, and the pointer to that memory is present in buffer. Now given this particular pointer, we can read or write or manipulate the data present in that heap chunk, and at the end of usage we can then free the buffer, and after the buffer is freed, that chunk of 256 bytes which we have just allocated in the heap can be used by other mallocs which may be present in the program. So what is the difference between a heap and a stack? As you know, stacks are used during function invocations and to pass parameters to functions, as well as for local variables. So stacks essentially are fast, they are fully managed by the compiler, and what we mean by this is that we do not have to explicitly have statements which say create a particular area in the stack and free that area in the stack. On the other hand, when you compile a program, the compiler would insert instructions that would allocate stacks, that is a stack frame, and free the stack frame every time a function is entered or returns respectively. As we know, stacks are used as a temporary data storage. So whenever a function returns, then the local variables which was allocated in that function is no more available. On the other hand, heaps are extremely slow. Every time you want to allocate some memory in the heap, you have to explicitly invoke the library function malloc, and similarly when you want to free that memory, you have to invoke the free call. So this management is done by the programmer, and quite often this could actually result in several different types of vulnerabilities, as we will see during this lecture. Heaps are used for storage of objects, large arrays, and global data, and typically if all you require is to have a pointer to that particular malloc chunk, and you would be able to access that malloc data from any function. So what we will see in today's lecture is how malloc manages the heap memory, how it allocates memory, what are the algorithms used for this allocation, similarly what are the algorithms used for freeing the memory, what are the data structures used internally, and so on. So there are a different variety of mallocs implementations that are present. The tcmalloc, for example, is from Google. JE-malloc is implemented in Android operating systems, and similarly you have NED-malloc and HOD. In all of these different malloc implementations, there is a subtle difference between the algorithms used to allocate memory and free memory as well. So essentially the algorithms will affect the speed at which memory is allocated or deallocated versus the fragmentation of the memory. So for instance, you may have one implementation of malloc which very quickly can allocate and deallocate memory. In other words, the time taken for malloc and the time taken for free is extremely small. However, it's as is generally what is seen, such fast implementations of malloc would quite often result in inefficient use of the heap memory. The concept of fragmentation of the memory sets in, by which there will be tiny chunks of memory in the heap which is not going to be used. So all of these different types of malloc implementations trade off between the speed of memory management versus the fragmented memory. By speed of memory management, we imply the speed with which malloc can allocate a memory, as well as the speed with which free can deallocate memory. Quite often it is seen that implementations of malloc, where malloc runs extremely fast, would often result in fragmented memory. So what we mean by fragmented memory is that there would be tiny chunks of memory, maybe of 2 or 4 or 8 bytes, which are too small to be actually used by any program. So these fragmented memory just reside in the heap and is of not much use. So essentially, when malloc implementations are made, they would have to trade off between the memory management scheme so as to reduce the amount of fragmentation present, at the same time ensure that the speed of memory management is good enough so that the performance of the application is not affected too much. Now these different malloc implementations also vary in the support that they provide. For example, the scalability, which means what is the size of the heap that the particular malloc implementation can manage. The other aspect that comes into play is the multi-threaded support. Can the heap implementation actually provide support for programs which have multi-threading present in it? So in this particular lecture, we will focus on one specific malloc implementation known as PTMalloc2. So PTMalloc2 is a very common implementation which is used in glibc. So most likely when you actually run your typical hello world program and you have a malloc in it, it uses glibc, and hence the malloc would invoke a function which is present in PTMalloc2. Now all of these different types of malloc implementations originate from one specific implementation by Doug Lee. You could actually search for Doug Lee and find the first implementation of malloc. Most other malloc implementations are derived from Doug Lee's implementation. So let's look a little more in detail about PTMalloc2. Note that while this is quite common in most recent day Linux systems, the third version of that, which is known as PTMalloc3, is also present. So there are subtle differences between PTMalloc2 and PTMalloc3, and we would not go into the details of these differences. In this lecture, on the other hand, we will be only focusing on the internals of PTMalloc2. Now, as we know, PTMalloc2 is present in the glibc library, which is linked with all standard C or C++ programs that you write on a typical Linux system. Now internally, PTMalloc2 uses two system calls to obtain memory from the operating system. So these system calls are known as break and memmap. So whenever break or mmap is invoked, so it leads to the operating system getting executed, and the operating system would allocate a chunk of memory for that particular process. So for example, if you write a C program and the first time you invoke the malloc's call within that C program, internally what malloc is going to do is that it is going to invoke the break system call. So when the break system call gets executed by the kernel would allocate a chunk of memory of size 132 kilobytes to the particular process. So that 132 kilobytes is used by the PTMalloc2 for its heap space. So within this particular area, you have different components. You have something known as an arena, then within the arena you have heaps, and within the heaps you have memory chunks. So whenever your program invokes malloc for the first time, internally ptmalloc would invoke the break system call, or the BRK. So when break gets executed, it causes the operating system's kernel to execute, and the OS would allocate 132 kilobytes of memory for that particular process. When break returns, the ptmalloc code would then have algorithms to manage that 132 kilobytes of memory. So that memory is divided into multiple different components. So the largest component is known as the arena. The arena is then split into heaps, and then there are memory chunks, right? So the memory chunks are present within the heap. Now let us first look of an example of how an arena is used. So let's look at this particular program. So as you see, this is a simple program which uses threads. So we have a statement over here where you allocate 1000 bytes and then return an address. Then you free that address. In this particular statement, you create a thread using the pthread library and invoking the function pthread_create. So this function would then create a thread which would start executing from this thread func that is present over here. So at the end of this invocation of pthread_create, we have this single process which has two threads, the main thread and the thread func thread. Now we invoke the pthread join in order to ensure that the main thread waits for the thread function to complete before continuing its execution. In other words, the pthread join would block the main thread until the child thread or the thread func completes its execution, and then the function would return. Now in the thread that we have just created, we allocate another 1000 bytes and then free that particular 1000 bytes. Now we will see what happens to the heap when we actually start executing this program. Soon as the program starts, it would be surprising for you to know that the size of the heap is initially 0. So essentially the program would start with absolutely no heap segment. Now when malloc first gets executed in this particular statement over here, it results in the ptmalloc code that we have been talking about to get executed. Now when this particular statement comprising of the first malloc of this particular program gets executed, it results in the malloc function present in the ptmalloc library to be invoked. Now the ptmalloc would determine that the heap segment is 0, and then it would invoke the break system call. As we have seen, the break system call would invoke the operating system, and the operating system would allocate a chunk of 132 kilobytes for this particular process. Now ptmalloc would obtain that 132 kilobytes. It would split it into two parts. Now one part is roughly around 1000 bytes and a pointer to this part is what is returned by malloc and assigned to address. So the remaining part is the free part. Now every subsequent malloc from the main thread would then utilize this particular free part of memory, and therefore subsequent invocations to malloc would not have to actually request the operating system for memory. So this large area of 132 kilobytes which the operating system has provided will then be used by all subsequent mallocs in the main thread until that entire 132 kilobytes is completely utilized. Now when this entire 132 kilobytes of memory is completely utilized by the main thread, a subsequent malloc would then invoke the operating system again and then get a new chunk of 132 kilobytes. So in this way you see that the operating system gets invoked only when there is no available space in the heap segment to satisfy a particular request. So what you see over here is the memory map of the particular process. So any Linux based system, if you actually cat this particular file, that is /proc/PID of that process /maps. It will give you the entire virtual address space for that particular process. In this case, the PID of the process is 1897, and therefore /proc/1897/maps would give you the virtual address space for that particular process. Now, at this particular point, when the execution has just completed malloc, so what you see over here is that after this particular malloc, a new segment gets allocated in the program. So this segment is the heap. Segment starts at 602,000 to 623,000, and if you can actually subtract these two, you would see that the size of this particular segment is 132 kilobytes. Also notice that you have read-write permissions for this particular segment, which means that you could read data from that particular segment or write data to that particular segment. In other words, it is a regular data segment. Code cannot be present in that segment because it is not an executable segment. Now, when the program next invokes the free function with that particular address, what we notice from the maps is that the heap segment is still present. Next, what we will do is we will free that particular address. In other words, we are freeing this 1000 bytes which has just got allocated. And what you would see from the memory maps is that even after freeing that particular address, the heap still remains the same. That is, even though the heap is not being used by this program at this particular instant of time. So what this means is that even though the heap is not being used after this particular point in time by the program, nevertheless, the heap segment is still present in the virtual address space of the particular program. Next, we will see what happens when you actually create a thread. So as we know, when you invoke the pthread_create, it results in a new thread getting created, which is present here. Now in this child thread, we malloc another 1000 bytes. Now it would be surprising for you to know that when you malloc this 1000 bytes, what happens in ptmalloc is that it would result in a new chunk of memory getting allocated. So within this particular thread, the first invocation to malloc in that thread would again invoke the operating system through the mmap system call and obtain another 132 kilobytes. So this entire area of 132 kilobytes, which is allocated by the main thread of the program, is known as the main arena. Now this main arena is split into various sub-heaps and used to satisfy various malloc invocations from the main thread of the program. Now let us see what would happen when we invoke the pthread_create. So as we know, the pthread_create would create a thread function, and the new thread would start executing this particular function. So in this function, we invoke malloc again and request for another 1000 bytes. The pointer to this 1000 bytes is then stored in this local pointer address. When the malloc from this thread gets invoked for the first time, what would happen is that the ptmalloc code would determine that this is a new thread, and this is the first invocation to malloc from that thread, and therefore it will request the operating system to issue another 132 kilobytes of memory. So let us see what happens when we actually create a thread using the pthread_create function, which starts a thread known as thread func. So the thread func starts to execute from this particular function. Now when we invoke malloc in this particular function, that is in the thread function, what would happen is that ptmalloc would determine that the malloc request is the first malloc request from the new thread, and therefore it would request the operating system for another chunk of memory. The operating system would then allocate another 132 kilobytes for that particular thread. So every malloc and free in this thread function will use this newly allocated region, right? So this region is also managed as an arena. Now we will look at the virtual address map for this particular process at the point when this malloc has got invoked. We will see that a new segment has just been created. The segment starts at 7FFFF followed by 7 zeros to 7FFFF0021,000. So you note that this particular region is also of 132 kilobytes. So every malloc that gets created from this particular thread would use this particular segment for its allocation. On the other hand, every malloc that is invoked from the main thread would use this segment for its allocation. So this segment is where you have the main arena, and this newly created segment is where we would have the arena for the thread, or the thread arena. So in this way, what we see is that it is likely that every thread we create in a particular program gets a separate segment. Now let us look at the entire structure of this heap memory. So as we know that one of the main components in the heap memory is the arena. So we have the main arena, which comprises of the arena which is used by the main thread of the program, and you could have various thread arenas corresponding to each thread that the process invokes. Now therefore, in one process we could have multiple arenas that are present. Now if you look at the PTMalloc2 code, we would see that there is a structure known as malloc_state, which is used to manage the arenas. Now each arena can have multiple heaps. So if you look in the ptmalloc code and into the structure called malloc_state, you would see that there is an instantiation of heap_info, which would actually be a pointer to a particular heap. So now let us look at the whole structure of how the heap is managed. As we know, the main component in the heap is the arena. One program could have one or more arenas which are present. Now each arena is of 132 kilobytes, and these arenas are created by invocations to the operating system. Now further, what happens is that each arena can have multiple heaps. Each of these heaps could be possibly non-contiguous. And if you look at the PTMalloc2 code, you would see that there are two structures that are present. The malloc_state structure is essentially used to manage the arena. So this is also known as the arena header, and it is present in memory and contains various metadata and other information to manage the arena. Similarly, if you look at the PTMalloc2 code, you also have another structure known as heap_info. So this particular structure present as the metadata would be used to manage specific heaps within an arena. Now each heap can have multiple memory chunks. So these chunks could be either allocated or unallocated, which is also known as a free chunk, and you could also have something known as a top chunk or a last remainder chunk. Now we will look at what a top chunk is and what a last remainder chunk is later on, but at this particular point of time it is interesting to note that the structure that actually manages this heap memory is known as the malloc_chunk. So you can look up the PTMalloc2 code and locate this malloc_chunk and see all the entries that are used to manage a particular memory chunk. So this particular slide shows the entire structure of the ptmalloc heap. So this particular entry over here is the main arena. So it is defined as the struct malloc_state. Now within this particular structure, there is an entry known as system map, which is a pointer to the main heap. So now the main heap is actually allocated over here. It is roughly slightly less than 132 kilobytes, and we have a top pointer which is pointing to the last block which is present in the heap. So this top pointer can be used to determine when this heap is completely full. Now every other arena that gets created would also have an arena structure. So we have an other arena displayed over here. So this is a thread arena, also known as a dynamic arena. So within this particular thread arena, we again have a struct malloc underscore state, which essentially contains the metadata for this arena that has just got created. So in addition to the main arena, a particular process could also have many thread arenas. So over here we have actually shown there are two thread arenas, one in blue color and the other one in yellow. So each thread arena is allocated to a particular thread in that process. So the thread arena is also known as the dynamic arena. So as we've seen before, each thread arena can contain multiple heaps. So these heaps are linked together by a linked list. So in each of these thread arenas, we again have the struct malloc underscore state, which is the management block which contains the metadata for this particular arena. Corresponding to each heap that is present in this arena, we have a struct heap underscore info, which contains the metadata for that corresponding heap. So in this particular example, corresponding to the heap present in blue, we have three heaps that are present. Therefore, we have three heap info structures. This is the first one, this is the second one, and this is the third one. All of these heaps are linked together but in a linked list, and the head of the linked list is this particular area. Now all of these various arenas that are present, such as this arena, this blue arena and this yellow arena, are further linked together by a linked list. So what you can conclude from all of this is that the entire heap segment of a particular process, it is not necessarily one contiguous segment. On the other hand, the heap segment in fact comprises of various smaller segments which are connected by linked lists. These smaller segments comprises of arenas, and each arenas comprises of heaps, and all of these are then linked together by multiple linked lists. Now the head of all of these lists is the main arena. Some more information about arenas in the heap. There is a maximum number of arenas that can be present in a particular process. Typically in a 32-bit system, the maximum number of arenas present is 2 times the number of cores present in that system. So these cores are the processor cores present in that system. In a 64-bit system, the maximum number of arenas that are present in a particular process is 8 times the number of cores. So for example, if I'm running a 32-bit program on a 32-bit system and the number of cores present is 4, it would imply that at most I could have 8 different arenas. So what this means is that if I spawn 7 threads in this program, then each thread, including the main thread of the program, would get a different arena. Now if I increase the number of threads in that particular program, then it would mean that you would have multiple threads sharing the same arena. Now therefore best efficiency and fastest malloc and freeze are obtained when the number of threads is restricted to 7 plus the main thread, so therefore 8. Now once you increase the number of threads beyond 8, since there is a sharing of arenas, it could result in a slight slowdown of the mallocs and freeze. This slowdown is caused due to the contention for using a particular arena. When a single arena is shared by 2 or more threads, the ptmalloc code ensures that there is synchronization between the threads in order to use the particular arena. So various locking and unlocking mechanisms are implemented in PTMalloc2 to ensure that the state of the particular arena is always consistent. So it ensures that when one thread is trying to use a malloc and that malloc falls in a arena which is also shared by another thread, then there is a locking mechanism to ensure synchronization. So something to think about. We mentioned in the previous slide that each process has a maximum number of arenas that are present. Now the question over here to think about is, why is there such a restriction in the number of arenas? What would happen if we have an unlimited number of arenas? That is, in other words, what would happen if each thread that you create gets its own arena? Next, we will talk about heaps which are present in an arena. The memory within a heap is split into memory chunks of different sizes, and these chunks are actually used when we invoke malloc and free. So the chunks are of two types. One is known as the allocated chunk and the other one is known as the free chunk. Now the free chunk is actually stored in a linked list. Now every time we do a malloc, let's say we do a malloc of 1000 bytes, what would happen is that the ptmalloc would execute, it would find the corresponding arena, and then it would determine the corresponding heap, and then within the heap it would find the memory chunk that could satisfy the 1000 bytes request. When such a chunk is found, then it would allocate that chunk to your process. So we will now look at how these allocated and free chunks are actually organized. So an allocated chunk looks something like this. When you malloc, say for example 1000 bytes, and this chunk gets allocated, the pointer that gets returned to the particular program is a pointer to this location over here. Now prior to this location there are some information known as metadata. This metadata could be either of 8 or 16 bytes depending on the system that you are running. So this metadata comprises of information about this allocated chunk. It has the chunk size which is present over here, and then it has three flags, the N, M and P flag. The P flag is used to determine whether the previous chunk over here, which ends at this particular point, is used or unused. Now if P equal to 0, then the contents of this would be the size of the previous chunk. Besides this, we have two other flags, the N flag and the M flag. So these two flags are not very important for us. The M flag is used to set if the chunk was obtained using an mmap system call, while the N flag is set if the chunk belongs to a thread arena. From a memory allocation point of view, when you allocate 8 bytes, it would mean that the 8 bytes start from here and end over here, and besides this there would be some more metadata bytes that gets allocated. So in a typical 32-bit system, you would have 8 more bytes that get allocated. So in total, for a malloc of 8 bytes, internally ptmalloc would actually allocate 16 bytes, 8 for the actual data, for the user data, and 8 more bytes for the metadata. Now when you free a chunk of memory using the call free and giving it the address, then malloc would actually convert that allocated chunk to a free chunk. And now the free chunk has a structure which looks like this. So what is important in this structure are these two entries, the forward entry and the back entry. So essentially what free is doing is that it would add this particular freed chunk into a linked list. So this linked list could be either a single linked list or a double linked list. And this forward and back pointers are used to point to the previous and the next free chunk present in the heap. So this is how it would actually look like. Let us say this entire thing is the heap, and within the heap you have various chunks. The orange color shows the allocated chunks and the blue color shows the free chunks. Now the lines over here, like this and these lines, are separations for the various metadata that are present. So important for us are these linked lists, which are used to store the free chunks. So over here we have shown a doubly linked list, which actually is linked to all the free chunks that are present in this corresponding heap memory. Now, whenever there is some malloc that gets requested, what happens first is that the ptmalloc code would parse through this particular linked list and determine whether there is a free chunk of memory that it can satisfy the request for malloc. If such a chunk is found, then that particular data is removed from this linked list and it is allocated for that memory. So thus you see, whenever there is a malloc that is done, it is likely that one chunk of free memory gets allocated. On the other hand, when a free occurs, one of the allocated chunks gets freed and gets added on to the linked list. The problem with this approach is that the linked list could be very large, and therefore malloc would take a long time to find the appropriate chunk to be allocated. So for example, let us say we have done a malloc of 1000 bytes, then this linked list has to be traversed until malloc finds one free chunk which is at least of 1000 bytes. And this could take a long time, and therefore what is actually done in ptmalloc is that we do not maintain just one linked list, but we maintain multiple different types of linked list. So we call this as binning. So in the ptmalloc code, in fact, you have various different types of bins, and each bin caters to different size of chunks that get allocated. So for example, over here we have a linked list of chunks which are of 16 bytes. On the other hand, we have over here a linked list of chunks comprising anything from 577 to 640 bytes. So now in this particular case, when a malloc gets invoked, it can directly go to that particular linked list and select the appropriate free chunk and allocate that particular free chunk much more quickly. In ptmalloc, there are different types of bins that are used. Most notably are the fast bins, unsorted bins, small bins, large bins. So besides this, we have something known as the top chunk and the last remainder chunk. Now, each of these different bins are managed in a different way so as to suit and best manage that particular memory. For example, the fast bins are a single linked list, they are not double linked lists. Now, each of these fast bins are in 8 byte chunks. So for example, we have fast bins of 16 bytes, 24 bytes, 32 bytes, and so on till 80 bytes. And also in fast bins, there is no coalescing. We will see what coalescing is at a later point. Essentially, coalescing is used to prevent fragmentation. However, if your bin happens to be in the fast bin, then there is no coalescing which is done. Now, since it is a single linked list, so there is a last in first out kind of operation which goes on. So this particular slide shows an example of fast bins. So in the main arena, we would have an array like this, and each array is a pointer to a linked list. For example, this first element is a fast bin pointer, and it's a pointer to a linked list of chunks which is of 16 bytes. This entry is a pointer to a linked list of memory chunks of 32 bytes, and so on. So whenever there is a malloc, say, of 32 bytes, what ptmalloc would do is that it would refer to this fast bin array. It would immediately get that it is a 32 byte request. It would go into this location and it would pick up the first available chunk over here. Now there's the linked list operation, wherein this location is now modified so as to point to the next available free chunk of 32 bytes. So you see that if your memory allocation is very small and it happens to be in the fast bin, then malloc works very quickly. All that is required is just to find the offset in the fast bin, pick out the first memory chunk that is present, and do a small linked list operation. So in this example, what we do is we malloc x, which is of 15 bytes, then print the value of x and then free x. Then we malloc y, which is of 13 bytes, print y and free y. So what happens when we execute this program is that both x as well as y, so there is a ceiling function which gets applied, and both of them would end up in the linked list corresponding to this 16 bytes. So when this particular malloc gets executed, totally a chunk of 16 bytes plus another 8 bytes gets allocated, and the pointer to that memory is present in X. So when this free gets invoked, the chunk gets added to the linked list corresponding to the fast bin of 16 bytes. Therefore, we would, corresponding to the fast bin of 16 bytes, we would have the chunk X that gets allocated. When we do a malloc of 13 bytes again after this free, it would actually obtain the same list entry. Thus, what would happen is that X and Y would get the same address. Thus, when we run this particular program, we get X and Y pointing to the same chunk of memory present in the process. However, this is not true if the sizes of the malloc are different. For example, if you do a malloc 8 and a malloc 13, these happen to fall in different fast bin entries. Now, on the other hand, if the malloc sizes are different, for example, here we have 8 bytes and then 13 bytes, then they end up in different fast bins. Thus, over here, X and Y would get different addresses. Now, besides this, we have unsorted bins. So this is one bin which is a double linked list that it could have chunks of any size. The allocation policy used by ptmalloc is to use the first chunk that fits. When a chunk is freed, it gets first added here. So this is an example of an unsorted bin. So what we see over here is that there is a double linked list. So therefore, there is a forward pointer and a back pointer. This is an array which is present in the main arena, and the element is of type bins. So you also notice that each of these bins are of different size. So for example, now if I do a malloc of 1000 bytes, it would come over here. It would find that 1004 bytes is too small to satisfy the request. It would come here and it would find out that 1008 bytes is exactly enough, and therefore this particular chunk would get allocated to that request. So let us see an example of the use of the first fit allocation which is present in ptmalloc. So what we do in this example is that we malloc two regions, one of 512 bytes which is pointed to by A, and the other of 256 bytes which is pointed to by B. Okay, then what we do is we free A and we malloc C which is of 50 bytes. Note that C is much less than the 512 bytes and the 256 bytes that has been allocated previously. Now what happens when we free A is that A is too large to go into a fast bin, and therefore it goes into this unsorted bin, and therefore the unsorted bin would have an entry which corresponds to the chunk of approximately 512 bytes. Next, what we do is we invoke malloc again with a request for 50 bytes, and the pointer that malloc returns is stored in C. Now in the first fit allocation, what would happen is the unsorted bin gets traversed. It would find that in this unsorted bin there is a chunk of 512 bytes that is present, and therefore what it would do is it would split this chunk into two parts. So one part is slightly more than 50 bytes, and this part gets allocated to C. Now the other part, which is not being used, will still remain in the linked list. Thus, when we run this program, this is what we would see. We would see that the initial allocation of A and B are at this addresses, and when we actually allocate C after freeing A, it would get exactly the same address that A has obtained. So you note that both address A and C are pointing to the same location, that is 9B10008. Now the other bins that are present are the small bins. There are 62 small bins which are less than 512 bytes, and there are chunks of 8 bytes present in them. These bins are also circular and doubly linked lists and satisfy coalescing. Okay, and it has first in, first out. So there are also 63 large bins of various sizes. The top chunk is at the top of the arena and does not belong to any bin. So it is used to service requests when there is no free chunks available. So whenever you do a malloc, what would happen is that the malloc would traverse through all the various linked lists, and if it finds that there are no chunks which are available in any of these linked lists which can satisfy that particular malloc request, then the part of the top chunk is taken and that part is allocated for the malloc request. Now, if the malloc request was large enough so that even the top chunk does not have sufficient memory to satisfy that particular malloc request, then the OS gets invoked and a new heap segment gets allocated. So this is done using the break mmap or the sbreak system calls. So in this way, we have seen how malloc is managed internally with various arenas, heaps, chunks and various types of bins. In the next lecture, we will look at more into detail about the free function call, essentially how free allocates and deallocates memory and how the linked lists are managed. And in particular, we will actually look at ways to exploit this internal aspects of malloc and how to actually create an attack on this scheme. Thank you.